Hello and welcome to today's BayesiaLab webinar. We're delighted to have you with us today. My name is Stefan Conradi, and in just a moment, I'll be joined on this virtual stage by my colleague, Dr. Lionel Juf, who will be your instructor for today's session. Before we begin, I'd like to draw your attention to the chat box on the right side of your screen. Please feel free to share any questions or comments throughout the webinar. We'll respond to some of the questions directly in the chat, and others we may highlight for Lionel to address during our brief Q&A breaks. Let me now add Lionel to the stream, who is joining us from his office in France. Here we go. Hi, Lionel. How are you today?
I'm good. How about you?
Good. Thank you for joining us. So, are you ready to roll with your presentation?
I guess so.
Excellent. All right, let's get going, and I'll turn over the meeting controls to you.
All right. So you can share my screen if you want, if you can. Okay, perfect.
Here we go.
Hello. Good morning, good afternoon, good evening. So today's webinar is about using BayesiaLab for drivers analysis. So this is already something that Stefan presented a couple of weeks ago. And this is obviously something we do since more than 15 years now. But we have obviously included Gen AI within this framework and also a new way to capture sensory expert data. So we are going to take an example. It was a study I've done in I guess it was like 12 years ago with French customers here about fragrance optimization. So this is the example I'm using also in the training session. So most of you should be familiar with this data set, but I have also included some generated open-ended questions or answers, more precise, to illustrate how we can use this text in order to improve, the machine learning algorithm that we have in BayesiaLab and have new kind of network, right? So yes, I was saying that we're starting with this slide that summarize for those who are new in this field, the BayesiaLab workflow. So we are, the specialist of Bayesian networks, and Bayesian networks is one of the main pillar of AI. And so this is the brain, if you will, of our probabilistic expert system. So it's a Bayesian network. It's a directed acyclic graph. So this is something highly visual. And here is, oops, I was afraid I mute myself again. Here is an example of Bayesian networks that we can now generate with Elixir. So it's still obviously something that we can machine learn, but now thanks to Elixir, our subject matter expert or assistant that is using, large language models, we can generate this kind of nice network. So I'm now used to call that the Bayesian network 3.0. So you see that you have icons, images that are associated with the nodes. So these are automatically generated with Elixir. And in this example, in this directed acyclic graph, I have links that have been, created. So they are causal and they are coming from Elixir. So from the knowledge that is embedded in the deep neural networks of the large language models, right? So you have the blue links that represent positive relationships, so positive causal relationship. And you have with this link a comment that describe the relationship. And when it's red, it represents a negative causal relationship. So here, very quickly, in this directed acyclic graph, we see that we have 6 variables: gender, age, height, weight, and BMI, body mass index. So this is an analysis that is based on US soldiers, right? And so with Elixir, we found that there is a causal relationship between gender and height. So when you are a man, you are most likely higher than when you are a woman. And the BMI is reducing with height and is increasing with weight. So this is what comes from the LLMs. And so for those who know already BayesiaLab, you see that we have, so in gender, so it's not only graphical Bayesian networks. I'm going to show you in a few minutes some graphs that are just qualitative, but here a Bayesian network is at the same time a qualitative network and a quantitative network. So when we dig into this network for gender, for example, we have exclusive states. So it's a discrete variable, if you will, with two states here, men and women. And if I click on probability distribution here, I am going to have what is the probability of having a man and or a woman in this domain. And this domain is described with a data set. So I have a small data set associated with this graph made of 520 soldiers, if I remember correctly. So even though I have extracted the structure, so the qualitative aspect of the Bayesian network by using Hedixia, so by using the knowledge of the NNM, the quantification of this network is done by using the usual parameter estimation algorithm that comes with BayesiaLab. So we are using the data for estimating or quantifying, if you will, the probabilistic relationship. So here we just have to estimate what is the probability to have a man or woman in this data set. So we are using just the occurrences. So we have 247 men and 260 women. So we just now normalize that to get this distribution. Then I have a link that indicates that I have a relationship between gender and height. And so this is, again, coming from Hedixia. And then I have a conditional probability distribution that is associated. But first, height is a continuous node. So in BayesiaLab, we are discretizing everything, but still the underlying dimension is continuous and ranges from, 147 centimeters to 198 centimeters, right? And we have discretized this variable into three bins, right, by using our automatic discretization algorithm. And then we have this then conditional probability distribution that depends on men and women. And same thing, we use the occurrences for the estimation of these probabilities. If I go on the node weight, we see that we have three incoming links. And so in a Bayesian network like that, the size of the parameters or the conditional probability table is increasing exponentially with respect to the number of pairs. So here we have three pairs. So we have a data set that is made of, three state for height, time, three state for age, time, two state for gender, right? And so we have this table that we have to populate. And then we use, again, the occurrences that are coming from the data set, but we can see that at the very bottom here, we don't have anybody. So there is no soldiers, if you want, that has a height that is above 180 and an age above 40 and a woman, right? So we don't have this combination in our data set. So if we had just used our usual machine learning algorithm, we would probably not have this link between age and weight, right? Because we don't have enough data. But then since we are using Hedixia for creating this causal network, we know that age has also an impact on weight. So this is like, expert knowledge. And then we are just using the data we have for estimating these conditional probability distribution. And then, so we have this directed acyclic graph with our variables that have exclusive state, can be discrete or continuous. We have the links between the dimensions, represent here in this example, causal relationships. And then we have also obviously the probability distributions that are associated with the nodes. And then once we have that, we have a fully specified Bayesian network that we can use as a probabilistic expert system, right? And now I can use it for inference. So it's going beyond just something like a knowledge graph or a semantic graph. Here we can really use it for computing probabilities. So now, what if I'm focusing on a man? So I'm just setting evidence on gender, and I set 100% on men. And then this information is used to update the probability of height. So what is the probability of being above 178 centimeters, given that you are a man? So it's 41%. And what is the probability to have a BMI that is above 26? Given that you are a man, it's 30%, right? Same thing. So we can also compute the probability of having or weighing more than 80 kilograms, if you want, given that you are a male. And here in this example, it's 45%, right? So the propagation is done from gender to all the other nodes except age here that is marginally independent. And I can also set evidence on one of the other nodes. So for example, if I set evidence on BMI, so at the very bottom of my network, I can say, well, now I'm focusing on soldiers that have a BMI that is less than 22. Then given this information, I'm updating the probability of weight, of height, of gender, and age. So the probability of weight given BMI being less than 22 to have a weight that is less than 63 is 80%, right? And obviously, I can mix any type of evidence. So I can set evidence on age and on BMI, and these two pieces of evidence are used to update the probability of weight, height, and gender. So we have the probability of gender given age being less than 28 and BMI being less than 22. And then in that case, we have 76% of chance to have a woman. And we can also add, an evidence on weight. So in that case, we are conditioning on three dimensions, right? And this is used to update all the probability of the other nodes. So this is, Bayesian networks that is now used by using the data set. So the machine learning algorithm coming with BayesiaLab and Helixia that is based on different NNN engines, right? So this was the brain of our expert system. So we can create this network by using machine learning algorithm. So we can use, data set and we have a large set of machine learning algorithms that are available in BayesiaLab that allows you to create automatically these networks. We can also use expert knowledge. So since directed acyclic graph is something that can easily be understood by the expert, we can use their knowledge and create manually Bayesian networks. And now we can also use Helixia. So it's a third way to create Bayesian networks. So either from scratch, or we can obviously merge or mix these three sources of information. So we can use Helixia to help machine learning algorithm. We can use Helixia for, during brainstorming session to improve the brainstorming session. We can use expert knowledge for biasing machine learning, and so on and so forth. So these three sources of knowledge are not exclusive, right? And once we have a fully specified Bayesian network, so again, the structure and the probabilities associated with the structure, we have a compact representation of the joint probability distribution of the domain we are dealing with. And then we can use it for decision support. So we can do, like I've done here in the simulation, in my example with my US soldier, we can do diagnosis, we can do analysis, we can do optimization, we can do risk analysis, and so on and so forth, right? So we are kind of the king of the world. We have model here. Now let's focus a little bit on Helixia, even though it's not the main topic of today's webinar, but it's quite important. So we have a different way to use Helixia. So the first set of function, if I want, is called the LLM knowledge mining. It's based on using the knowledge that is captured or encoded in the deep neural networks of the LLM engine to create graphs. So we can use a dimension elicitor. So it's a feature that allows to identify what are the important dimensions we need to include in our model. And then once we have this dimension, we can create embeddings and machine learn with BayesiaLab semantic networks. We can also, based on the dimensions that have been extracted, find the relationship between the entities, and then we have a knowledge graph. Or we can also use the dimension that have been elicited and then create or estimate or identify the causal relationship that we have between these dimensions and then generate a causal net. The second way is to start from scratch, and we can then use Helixia for directly creating a semantic flowchart, a causal semantic diagram, or a knowledge graph. We can also create causal network or risk-centric causal networks. So this can be done with or without knowledge file. So when we have a knowledge file, so it can be an article or a set of articles, it can be a book, it can be anything, but we just associate with with Helixia context, and then Helixia will take this information into account in order to create the graphs, right? So this is the first set of function. Then we have what we call the LLM augmented machine learning. So this is when we are using Helixia for improving, machine learning algorithm in BayesiaLab. So it can be for identifying causal relationship between the nodes. It can be for estimating priors on the nodes, on the connection we already have. It can be used for clustering. So we use it for clustering variables together, but we can also use it for associating names with groups of variables that have been clustered together. We can use them for creating labels for the states that comes from segmentation when we do data clustering. So it's a very, very useful set of features. Then we can also use Helixia for helping brainstorming sessions. So this is our brainstorming assistant here. So it is used for, when the experts are giving us a set of dimensions. So we end up usually with a set of 20, 40 different types of dimensions. So we use Helixia for creating a semantic network based on this dimension. And this helps for, choosing, for selecting what are going to be the dimension we will include in our network, right? And then we can also use Helixia for the estimation of the probabilities. So when we use ICI, independence of causal influence type of network, then we can use Helixia for eliciting root priors or eliciting, the local effect, the direct effect of the variable on the target. So this I'm going to show you in a few minutes. And Helixia obviously is also able to create informative comment summary based on the different comments that are associated with all the priorities that have been elicited. So very useful for the subject matter expert that have, at the end of the day, also to elicit the probabilities, right? Then we have the LLM text-driven causal discovery. So this is based on a knowledge file that we are going to analyze. So by using the first set of features I already mentioned, the knowledge mining, we use that for one of these different graphs for extracting useful nodes. Then based on this node, we create an ICI network, and we use Helixia for the estimation of the root priors and local effect. So this is the example I'm going to show you at the end of this webinar. And the last set of feature is for documentation. So this is a set of features that allow us to, create comments or associate comments, very useful comments with the nodes. That's very, very important for having something that you can really exploit at the end of the day, because usually a week or 2 weeks after having a network, you don't remember exactly the exact definition of each dimension. So now with Helixia, we are able to capture this. We can, have some kind of verbalization of the relationship between nodes, description of the relationship between the nodes that have been machine learned, for example. We can generate long names, we can generate images, we can analyze or create a textual report on the report that describes the network. We can translate all the components of the network in different languages. So very, very convenient set of features. But let's talk about our example for today. So this is, again, the analysis of a data set of perfumes. So we have, at the very beginning, we have 12 products. So now I think I just kept 10. And so each product have been evaluated by a set of 120 customers, so women here that have evaluated. So only one product per woman. And then we have to use this feedback for trying to find what are the best drivers that we can use to improve it's not here really the purchase intent, but something very close to that. And then we are going to see how we can use this data for optimization. Then we are going to see how we can include, the data that comes from trained experts. So it's usually another data set that we cannot merge with this one because it just use different set of variables. The trained experts are usually, less than 10, and they are evaluating more than once each product. And so it's not easy, but this is really the data that we can use for the optimization, because this is highly technical, right? So now we are going to see how we can use this expert data for the optimization of our product. And we are going to also see how we can use, open-ended feedback from the customers for learning relationship between the different dimensions. And also at the end of the day, estimate or quantify the effect of each drivers, right? So this is a schedule. So for this, we are going to define or use a probabilistic structural equation model, so a PSEM. So just as a reminder, a PSEM is just one click. In BayesiaLab, it's a workflow. So we first have to start with, a network that represents the relationship between the answers given by the customer. So this is what we call the relationship between the manifest value, right? Then once we have this network, the second step is to analyze the network we have created in the first step, and to identify what are the clusters of values, what are the values that are strongly correlated, and that probably, represent a kind of hidden concept, right? So this will allow us to remove or to take into account the redundancy between these values. And then we are going to create this cluster of values, identify them. Third step is going to be to create one latent variable per cluster, right? So in the second step, we have identified 2, 4, 6, 8, 10 clusters here. So we are going to create 10 different latent variables that will really technically represent the hidden concept. So this is what we call the factor, right? And then these factors are at a higher level, if you will. And at the very end, we are going to learn a hierarchical Bayesian network. So at the bottom, you have the manifest variable. At the top, you have the factors, so the hidden variables that we have constructed, if you will. And they're going to be connected with our target node. And we are going to use this hierarchical approach for the optimization. So this allows to take some distance from the manifest variable where we can have lots of noise. So here, by analyzing this hidden variable, we are going to have something much more reliable, much more stable. But let's start with the first step, right? So we are going to try to identify what are the relationships, the strongest relationship between the answers given by the customers. So for that, we are going to use the BayesiaLab 11.6.1 here. So just the information, we have released yesterday 11.6.3. So if you have a license and if you have technical support, you can always go to help and see to check the new version, or you go to the website and you can here check if you have access to the new release. Right. So here I'm going to start by obviously opening the data set. And we have the first results. This is for, the defining what are the variables we're going to use. So we have the first column is called cell, and it's representing the different products. So we have 10 different products, and I'm setting here this variable as a discrete variable. So when it's turquoise, it's continuous. When it's red, it's discrete. So the second one is going to be our target variable. It's a 6-point Likert variable. So we are also going to discretize it, or at least not discretize it really, but assume that each state is really independent. So we are not going to merge discrete states together or continuous values together. All the other one are 10-point Likert variables, so from 1 to 10. And we have this one, the intensity, that is a just about right variable with 5 values. 1, it's not strong enough. 5 is too strong. 3, it's perfect, right? All the other one, as I said, are Likert variables. So from 1, I totally disagree with the statement. 10, I totally agree. Right? Then we are going to manually discretize all the 10-point scale variable, because we have to reduce the number of states here because we don't have lots of data. And for that, I'm going to just manually define the discretization. So 1, 2 together, 3, 4, 4, 5, and so on and so forth. So I create these thresholds here for one variable. So I'm taking the first one. And then I'm going to manually set the threshold. So one threshold at 2, another one at 4, 6, 8. And then I'm going to select all the node and transfer this discretization to all the nodes, right? So this way, my 10-point Likert variables are going to use the exact same thresholds, right? Very convenient, right? So I do finish, and then I had my Bayesian network. So I had one node per column in my data set. I'm just going to do a quick sanity check here. So I'm selecting all the nodes and double click on them to get the monitor. And I can see the different thresholds that have been created here. So I can see the distribution on these variables. I have cells with 10 different states from 1 to 12. And then I can see the distribution, right? Now I'm going to define classes because we have different types of nodes here. So here I have a dictionary. So it's just a pure text file here. So decode classes. And in this text file, you see I have the name of the variable equal then the name of the class I want to define, right? So I'm just associating this file. And then I have my screamer icon at the lower right corner, and I have my 4 different classes. So I have target with only one node. I have evaluative variable, 28. I have then the product, one variable, and projective variable, 19 projective variables. I can select all these classes, define and associate a color with all these. So now I can quickly identify my nodes by using the color, right? And since I'm focusing on the first step here of the PSEM, I need to machine learn the relationship between the manifest variables. So I'm going to use only the evaluative and projective variables. So I'm going to exclude the product. And after that, I first need to do a first step of analysis. At the very end, I will also exclude the target. But for now, I'm keeping it for machine learning the relationship with all the nodes just to gather some knowledge or discover the knowledge. So I'm using EQ here. So in that case, it's an unsupervised machine learning algorithm, which means that even though I have a target in mind, I'm not defining this as a target. So I'm really trying to discover all the main relationship between these variables. So I'm layouting this graph. And I can see that I have some blocks of color. So in order to have a better visualization, I go to node force. So it's a very convenient way to represent the networks here. And so here I can then look at my nodes. So the size of the node is proportional to the strength. So the strength is, if I have information, so here you see the biggest node, it's a fragrance I could wear with pleasure. So this means that when I know exactly what is the answer on this question, this allows me to reduce the uncertainty on lots of nodes. But if I have information on, for example, at the very top here, the woman who wears this haute toilette is classic. Well, I'm going to be able to reduce the uncertainty on this fragrance is classic, but then after that, it's fading away, and I'm not going to have any impact on the fragrance. It's easy to wear, for example. So in blue or gray, I don't know what is exact color, we have the evaluative variable. Then in yellow, we have the projective ones. And then you have in a little bit, it's almost yellow too, but it's a target. Okay. So first information, pleasure is the most important dimension in this domain, which is not really surprising since we are talking about fragrances, right? So now there is something that we can do is we see that we have evaluative and projective variables. So we're going to see if we can find more useful information that's the one we can see right now. Because here we see that when we have a connection between a blue and a yellow, at the bottom, you see this fragrance is modern and is connected with the woman who wears this perfume is modern. So it's not really surprising. Then we have fragrance evokes sensuality that is connected with the perfume is sensual. So there are kind of obvious relationship. And then we're going to try to find something more useful than that. So we are going to have to define some constraint for that. So we just exit from this mode. And then we are going to use here as a constraint definition. So here it's by using edit forbidden arcs. And I'm going to define that here the projective variables cannot be parents, right, of any nodes. So I'm really forbidding any outgoing arcs from the projective variables. And then I'm relearning the relationship in my network. And this will obviously change the structure. And if I go back to the node analysis, I have now something that is more useful, right? So for example, sensuality is still connected with sensual, but it's also connected with the woman where this perfume is seductive, is romantic, is passionate. If I go and look at the good mood and joie de vivre ici, I can see that it's connected with the perfume is approachable, that the woman where this perfume is also fulfilled, blossoming, happy. Then if I see high-end perfume, I see that the woman who wears this perfume is bold, is self-confident. So it's much more interesting than the very first network we have, machine learning, right? So for enhance my value, it's now I'm even dynamic, I'm optimistic, I'm radiant, I'm in love. So very, very informative, right? So now that we have done, so here it was more like a kind of exploratory step. Now we are going to exclude the projective variable because at the end of the day, we are not going to be able to improve them. So they are not representing any drivers, right? So we're going to exclude the projective and the target node. So we exclude the first one, and then here just make a right click on one of the projective one and exclude the nodes that belong to the class. And then we relearn the network by using this subset of nodes. And at the end of the day, it's the same one. We can see that we still have, obviously, the most important node being a fragrance that we wear with pleasure, right? And then by using the slider, we can conduct a kind of analysis that goes from the strongest, the most important node to the least important one. So the second one is the fragrance is elegant, refined. Then it's enhance my value. Then is I have. Then will please my friends and family and so on. Right? So this is the first step. So have machine learn the relationship between the manifest variables that can be used for, at the end of the day, as a basis for my product optimization. So second step. So this is when we use a network with just machine learning. We analyze it for, finding what are the concepts, the hidden concepts that are here in our domain. So we are going to use for that, variable clustering, and then use Helixia for generating the name of the concept, right? So usually it's something that is not easy because you have to find a name that is based on the set of nodes that are grouped together, right? So we have our network, so the one we machine learned just before, and we are in validation mode, and we go to variable clustering. We set, we don't set any maximum numbers of clusters. We check the option processing of diff node and generate a cluster name with Helixia. Then you can choose a completion model you want to use. So we have a large set of models. So I'm using by default Anthropic, but you can use OpenAI, you can use Gemini, Google, you can use Llama, you can do DeepSeek if you want, or your own endpoints if you have some. You define, the context. And here it's important to have a knowledge file because you really have to indicate to Helixia, what are these values? What do they mean? So for example, we have Likert scale. So Helixia, it does not know if 1 is better than 10. So here we have this very simple text file that describes the domain or that describes the questionnaire. So 1, 2 strongly disagree, 8, 10 strongly agree, and also some information for the just about right value. So 1 much too light, 5 much too strong. So thanks to this knowledge, Helixia will be able to analyze a relationship and find useful names. And then we have also a general context, so fragrance survey analysis. Subject of query, right now we just have node name, so that comes from the questionnaire. And the language is English, and we just set by default a short description for the name of the concept. So this is generating the concept here, so the clusters. If we click on the dendrogram, so we found 5 clusters. So we have these dendrograms that represent the clustering. And at each possible clusters that have been generated, we have a name that have been generated to summarize the concept represented by the group of variables, right? So if we switch to the mapping view, here we have the 5 clusters that are illustrated with the name. So the most important one is called the wearability satisfaction. Then the second one is luxurious refinement, and so on. If we just go to, use the sliders here, we are going to be able to, to see how our hierarchical clustering works, dynamically. So if I set 28 clusters, this means that I'm just representing the initial graph. So this is just the relationship between the manifest values. So our hierarchical clustering algorithm will first start by merging the 2 nodes that are associated with the strongest relationship. And these nodes are, this fragrance suits me well, and it is fragrance that I'm going to wear with pleasure. So this is the strongest relationship. And then if I go to 27, we see that it has created. So if I go back a little bit, you see that now this is the cluster name self-identification. So we merge these 2 nodes and then create a new virtual variable called self-identification, right? And then we continue. Then after that, we have the emotional uplift, external validation, premium quality, patient forward, and so on and so forth. So we are dynamically creating these clusters. And for each cluster, we have a name. And when we hover over a node, we have the list of the variables that have been associated with the cluster, right? So we validate this, and we have this report where we have 2 different tables. So the first one is a list of the factors. So factors, the name, short name, like factor 4, and the long name, fashion forward identity. And the second one is the list of the nodes along with the classes that have been associated with the node. And if we go to the screamer here, we see the list here of the factors that have been created. If you are not satisfied with the name, which obviously can happen easily, you can always regenerate the name. So either by changing the engine or just by retrying, because it's not deterministic. So here we have a second name, right? So this was the second step. Let's continue, third step. So now the idea is to create the nodes that are going to represent the concept. So we're going to go just from, the second step was the identification, the definition of the concept. Now we are creating the node, right? So for that, we are going to use also Helixia, but now for creating names or associating name with the state of the hidden variables. So we go to learning, multiple clustering, because this is done by a data clustering. Here we are going to define an output directory. We define this option as usual. And then we are going to check the option, generate cluster name with Hedonic, right? And then on the right, you have the setting for the LLM. So same thing, we're going to use a knowledge file, the context, and then the description length. So here we have 5 clusters of variables, so which means that we are creating 5 different nodes here. And at the end, we have this new graph. We go to step of sanity check here, and we see that, for example, the first cluster, the green one here. So the name of this cluster is luxurious refinement. And we have 5 states that had been automatically named. So we have luxurious femininity, floral elegance, neutral, underperformer, fragrance rejecter, uplifting elegance. So these have been automatically created with Elixir by, analyzing the clustering results here, right? So this is based on this fragrance enhanced by value, elegant, refined, joie de vivre, feminine, rich, and so on, right? So this is, for example, when I'm focusing on women that have been qualified as luxurious femininity, then we see that they agree with the fragrance enhanced by value, they agree on elegant and refined, and so on, so forth, and they agree, obviously, on the perfume is feminine, but not really on spicy, right? If we generate the analysis report for this specific node, we're going to be able to see a mapping of these states. So here we have a representation, a 2D representation of these 5 different segments of customers. So on the left, you have the rejectors, and on the right, the luxurious femininity. So it's like having an x-axis so on the left, you have the disagree with the 6 statement or 7 nodes here. And on the right, they agree with this statement. Okay, so let's here, if we generate the report again, we can see that with the color. So you have an analysis of each state. So luxurious fluidity, you see everything is dark green, which means that they all belong to the state 8, 10, or not all, they're mainly associated with these states. When it's red, it's the states between 2 and 4, for example. And yellow, it's 4, 6. And dark red, it's 1, 2. If we check this one, the pink one, so indigent allure, we see that we have 5 states. So in this hidden node, and we can see that we have 2 states with the same name, sensual pleasure, right? So which is not really convenient. So it's okay here because it's only long name, because obviously you cannot have the same names in the same dialog, but the real state name are not these ones. So these are only long names. So we don't constrain anything on, we can have the same name, but obviously it's not convenient for communication. So we are going to see how we can regenerate this when it's not satisfactory. And here, obviously it's not. So we just we click on the node, then we are going to select generate state or name. We choose again the engine that's going to be used by Helixia, the knowledge file, and so on. And then we have another set of names, right? Then if it's still not satisfactory, we can either change the engine, or we can decide to increase the description length. So a slight increase here. And then we are going to have perhaps 3 words per state, right? So have more information there. All right. Any questions?
Yes, we do have a question. I'm bringing up a question from Stephen. I think you have answered it already a little bit. The question is it possible to get further definition of the states of the clusters?
Yeah, in this case, you just have to increase the description length, right? So if you set it to its max, you're going to have a large description of the state. Or even if you uncheck it, it's going to be the default value. So it should be long enough to describe the states. Okay.
All right. Thanks, Lionel.
Okay. So 4 steps. So this is when we are gonna now complete, the learning of the hierarchical model, right? So we are gonna machine learn the relationship between the latent variable, and we go there. So we just, oops. So we are gonna bring back the target node. Then we are gonna machine learn the relationship between the target node and the new node that we just created, right? So it's we are really at the upper level of our graph. And then we have this network where the target is connected only directly to one node, so wearability satisfaction. And in our analysis, we are going to assume that these latent variables are not directly observable, right? So we're going to just define here a cost. So we just have to make a right click on one of the node of the latent and define a cost that is. So we just uncheck it to define it that's not observable, and we propagate it to all the latent. Then we go to validation, we do sensitivity analysis, and we are going to see a first view of the total effect here. So we see that since the target is only connected to the blue cluster here, wearability satisfaction, obviously, the nodes that belong to this cluster are those that have the strongest impact on the target, because the longer the path is to the target, the weaker the relationships are, right? So this is the first information. Then we can generate this kind of quadrants. So it's more graphical. So this is another view of the tables, but it's graphical. So with these little triangles that indicate that you have to increase the value. Here, what it's the blue triangle for the fragrance, the intensity means that you have to decrease the intensity to improve the lighting here, right? And when you, for example, the just about right has a scale from 1 to 5, so not the same scale of as the other one. So if you click on normalize mean, you can have the same scale for on the x-axis here, right? And we see that woody and spicy, since it's a perfume for women, are at the very bottom here. It's not really feminine. So since we just have one connection with a latent variable, sometimes it can be convenient to force a little bit things. So we are going to directly connect or create a kind of semi-supervised network, and we're going to connect manually the target node directly to all factors. So we select here the node, make a right click, and we say that the target node is a parent of all the factors. Then we go to parameter estimation for estimating the priorities. And then we have this network, right? So now we are assuming that we have a connection between the latent and also a direct connection of the target with all the factors, right? Then we go through the same kind of analysis as before, and we see that the order is more or less the same, right? So the unsupervised learning was not ready, but you can see. But it can be reassuring sometimes to have this direct connection. Okay, so we see that the mean value of liking is 3.7. And if I set an evidence, I'm focusing on the woman who say, oh, this is a fragrance I don't wear with pleasure. So in that case, the mean value, the liking is decreasing to 2.5. And if we set focus on the woman who say, oh, yes, I fully agree with that, then we have liking of 4.5, right? So this is how we can use this network here right now for inference, basic inference. So now what we have done is a network that has used 10 different products, right? So for optimization, obviously, we cannot use directly this one because it does not represent one product. So we need to create as many network as product in our data set. So we are going to first start with a segment analysis here. So we go to, we are going to bring back 7, sorry, because this was not there. So this is variables that indicate what is a product, right? From 1 to 12. Then we go back to validation. And we go to segment, profile, impact on targets, right? And then we are gonna, here I'm using the standardized total effect, but I think it's better to use total effect. I don't know why I use it here, the standardized version, but anyway, it's more or less the same thing here in this example. And then here you have this very nice representation that indicates the pros and cons of each product. So when it's green, this means that these dimensions are very, like, strengths of the product. And when it's red, you have the weaknesses of the product. So this is for product number 1. Then if we switch to product number 3, we're going to see another profile. So this one, you see, is not a good product. Product number 4 is so. Then we have the 6 here, same thing, 7. So you can go through all the product and have a visualization of the qualities of your product with respect to the population of products, right? So, and here it's based on the standardized total effect. Now we are going to create one network per product. So we use a multi-quadrant for that. So we define these options. We are going to save each network in a specific directory. And then, so in this multi-quadrant, also based on standardized direct effect in this case, you can also check the boxes and see the direct effects of each product, right? So for each product, you have a quadrant, right? So this allows you to compare the products. When you hover over a triangle, you can see where or how the other products are with respect to this one. You can check this option, show landscape, so that will, so this is a representation on the x-axis. You can see the range of all the products. And then you can also use this representation to really highlight the range. So this is for the mean value, and you can have also the vertical one for showing the range of effects of here, direct effects, standardized direct effects, right? So now what I'm going to do is I'm going to export the mean values here. So this way I'm going to see what are the best and worst mean value in this set of products, right? So, and this is something I'm going to use for generating realistic optimization strategies. And I'm going to focus on product number 1. So I'm choosing the file multi-quadrant one. And then, so I can see that I just have product number 1. So the mean value for product, the liking is 3.8. And I'm going to define what are the drivers for this domain. So, because I cannot improve all these dimensions. So I have a file here that is called decor cost, where, for example, this fragrance suits me well. This is not something I'm going to be able to directly improve, right? So this is not a driver per se. So I can improve, I can change the intensity of the fragrance, but I cannot change directly suits me well, for example. So I have these drivers, and then I'm going to use them for my optimization. So I'm going to use here dynamic profile. And then this indicates that the fragrance, I need to start with, original. So if I'm able to make everybody happy, then I'm going to increase the mean value to from 3.8 to 4.5. But obviously, so if I go to the scenario here, this is not something that is realistic at all here. I'm not able to change the product to be able to, yes, to have 100% of my customers that are happy with this. So it's absolutely not realistic. So I'm going to just define or use the ranges I've exported before. And here go to numerical evidence, associate my ranges here, and then use them to simulate realistic policies, right? So I'm going to say, oh, I see that product number 6 is able to reach this value. So I'm going to simulate this. And in that case, now I have these two drivers that I need to improve. I need to improve freshness and then fruity, right? And if I look at what happened on the segment I had before, so this is as a result of this optimization. So freshness and fruity. I can also generate a tree. I'm going to go real quick on that. And here, so we find the same drivers. So you have set a large set of optimization policies here that allows us to create a report that rank the drivers here that can be used for the optimization of product number 1. But we see that when we summarize these trees, this is really fruity and fresh are the top drivers. And we can include also floral. And if we go back to the segment analysis we had at the very beginning, we can check that indeed for product number 1, we had fresh and floral where the lowest, the worst dimension in this for this product, right? And fruity was not that far. So then here it's how we can, use another data set. So the first data set I used was, coming from the customers. Now I'm going to use the one that comes from the experts. So it's totally another data set, but that is much more technical, right? And so here I'm going to open the data source. So it's a data that is obviously much smaller. So here you see I have only 160 rows and I have only 9 experts. So the idea here is and I have multiple evaluation for each expert and products. So each product has been evaluated perhaps 4 times or 6 times by each expert. So I need to normalize. So I've used the Z normalization for that. So this way, the mean value is 0 and the standard deviation is 1. So when it's positive, it's above the mean value of this given expert. When it's negative, it's less than the mean value for this expert. So we do that for each expert and each column, right? And then, so everything obviously is continuous. So I'm going to quickly here discretize my normalized value here. And I do that manually. So the idea is to say, okay, I want to have 3 states, one that is less than 0 and the one for above 0. And if I have some 0, I'm going to also have a third bin for the 0, right? So I'm creating this manually. I'm propagating this to all these variables. And then I'm going to, again, as usual, do a sanity check. And here, what I want to avoid are these. So as you can see, I have 5 or 6 variables for which the 0 bin is empty. So I don't want to have a state that is useless, that don't have any data. So this is just adding complexity. And since I don't have lots of data, I want to get rid of that. So I'm going to rediscretize these 6 variables. Okay, so I'm using the binary mean for that. And then I have nodes with 3 states, others with, and then I exclude respondents themselves, and then go to semi-supervised. I'm going to create a semi-supervised network. So first I'm learning the relationship between these nodes and include the library cell and connect this library to all the other one, right? So I'm creating a class here to be efficient, and then connect this node to the class sensor, do parameter estimation, and then I have this naive or augmented naive, if you will. That. So here I have my product that is connected to all the dimensions that have been evaluated by trained experts, right? And here, so if I want to merge yes, I have one data set with the customers, another one with the expert. And the problem is that there is no way to make a juncture between these two data sets. So the only variable that is in common is sell, the product. So now what I'm going to do is I'm going to just go back to my previous network, right? So I'm going to go back to my network that based on the customer. I'm going to manually add a link between sell and my target node. So I add a link from sell to liking here, go to parameter learning, and then copy this node. And I'm going to just paste it in the other network, right? So here I'm taking one part of the network from the consumers, and I'm pasting it in the network of the experts, right? So I don't remove the data set. And then I have now one node that comes from the customers, and that will allows me to estimate the liking of customers based on the HUD that is here, cell, right? And then if I go to, I'm just setting cell as not observable, and go to target correlation, and I see that vibrant here is the most important dimension, expert dimension, for explaining consumer liking, right? So you can see that the relationship is not really super strong, but we do have a relationship. And then if I can carry out the exact same analysis, segment analysis here, but by using expert dimensions. And then we have for each product now, the strengths and weaknesses of each product, but expressed by the dimensions that have been given by trained experts and not just customers. Okay, so this can be used for now the technical optimization of the product. So let's switch to the part where we are going to exploit or use, the feedback that comes from customers that have been written, so it's like open-ended questions. So we have these kind of variables here, the comments, and we are going to use Helixia for analyzing this text, right? And we are going to use here the left part. So using the comments as a knowledge file for identifying the structural priors that will allow us to bias our machine learning algorithm, right? So this is this specific part. Our data set here. So here I'm I'm focusing on one product number 6. So I have the node that comes from the subset of data. So I'm just have the data. So I have 120 samples here. So the women who have evaluated product number 6. And if I do use machine learning on this data, I have this network where you see, if I use my layout algorithm, we're going to see that first we have some orphan nodes, so nodes that are not connected. And no, we don't have some network in this one, but we have lots of nodes that are unconnected, right? So what we want to do now is to use the comments in order to see if we can exploit the information that is contained in the comments for trying to have perhaps from new relationship or, change the ones that we have machine learned and that we are just relying on 120 feedback or data, right? So we go there and we are going to use the causal relationship finders that is using, a set of engines. So here I'm selecting 5 engines. So I have OpenAI, I'm going to use Anthropic, I'm going to use Google, DeepSeek, and so on. So I'm going to use these guys for, trying to identify causal relationship between these these nodes. And so I have this as a knowledge file, and my general context here indicates that I have 120 feedbacks on fragrance survey analysis. So it's important to indicate the number because this allows Elixir not to have to count them, right? So this way, it's better, right? And then I'm gonna create, or the result is gonna be just total coefficient. I'm not adding all the links to my network directly. So I have at the lower right corner, you can see I have these icons that indicates that I have structural prior. And when you click on that, you have a list of all the structural priors that have been found, right? So we see that the fragrance is timeless. It has a causal influence on this fragrance is for all women. And so this is given by Claude 3.7, right? Then when you we can sort them, have a preview here of all the relationships that have been found, right? And we can also find here a way to sort this by a number of assessments. So if I click here, I have, for example, 3 engines out of 5 that found a causal relationship between the intensity of the fragrance and the fact that it's easy to wear or not, right? And so we have the prior value. So if the prior is equal to 1, this means that we are 100% sure that there is a causal relationship. And then the cost for BayesiaLab to add this link is 0 at the end of the day. Right? So the higher the prior is, the less expensive it is to add the link, even though the relationship in the data set is super weak. Right? Then we have this total prior, and we are going to use them along with Tableau for machine learning a new network, right? And this is the network we have by using simultaneously the data and the information that comes from the comments. And if we have a look at the mapping here, so we see that the strongest node is this fragrance is high here. We see that we still have orphans, but less orphans than before, right? So this is an illustration of how you can use open-ended comments for, helping machine learning algorithm to take into account this information. Now, I still have 2 topics to cover really quick. So the first one is how to use the comments for, knowledge discovery, if you will. So not just for helping machine learning algorithm of BayesiaLab, but really for you, just to see what are those comments. So we are going to use here the LLM knowledge mining set of features. And more precisely, we're going to use the semantic network and the knowledge graph. So the semantic network or causal network instead of knowledge graph, I think. So I'm using here the document analysis, using the engine, setting the comment file. So you see you have a warning because if you use a public LLM or public external LLM, you're going to send this data to these guys. Then here we can have a preview of the data, right? So very important to see if everything has been properly converted. Then we have the general context. And here, this is the semantic network is always based on dimension elicitation. So elicitor, so which means that we are using a set of keywords, right, for identifying the useful dimensions. So here I'm using a predefined group of keywords that is the domain definition here, where we have 10 keywords that have been defined. So you have indicators, you have all these things, factors, features, criteria, and so on. So here, this is the networks that have been extracted from this set of comments. And if we go to node force, then same thing, we can see this net. So this is really the analysis of the 120 independent feedback from the customers here, right? And so feminine is the most important dimension in this case, right? Okay, so this is a semantic network. Then we're going to create a knowledge graph. So we go to document analysis and generate a knowledge graph. And here, so you have fragrance. So you have the root node here that receive positive feedback, neutral feedback. Then you have also negative feedback here on the left. then you can see that the negative feedback are sometimes caused by the strength of the fragrance. Then you have the fresh notes that enhance the wearability. Then everything here is impacting the repurchase intent. Uh, uh, then you have, the positive and neutral feedback, obviously, that have the same kind of impact on the repurchase intent. So positive feedback is influenced by the longevity, the uniqueness, mood enhancement. So you have a description here via a knowledge graph or of your set of comments. And finally, I'm going to create a causal semantic diagram here. And so this is now causal, right? So you have the fragrance that demonstrate longevity, that exhibit intensity, that affects wearability, that affects overall impression, and that at the end of the day will determine the repurchase intent. So overall impression and longevity are those who are impacting the most the repurchase intent, right? Let's go to the final one. So this is when we also want to use these comments for creating a causal graph that's going to be used for ranking the drivers. So we're going to really mimic what we do when we do brainstorming session with really human experts. Instead of having human expert here, we have these independent feedbacks, and we are going to use Helixia with this feedback to create an ICI network. So a network where we are assuming that all the drivers have an independent effect, right? So we are going to use a knowledge files that are going to be based and used on the knowledge mining set of features of Helixia that we are going to use for extracting the useful nodes and then create our ICI. So here we go to Helixia, and then document analysis, and then semantic network generators. And we are going to extract nodes just by using two keywords, the pros and the cons. Right? Then we are going to extract these dimensions. So we have two colors, one for the cons, one for the pros. We have data that is associated with that because these nodes are continuous because they are based on the embeddings. And so you have the dimension along with the comments, and then you have relationship between these nodes, and these relationships are semantic relationships, right? So based on the embeddings, right? So for the ICI, we have decided just to use the pros, right? Not the cons. So we have these nodes, and they're going to be used just for trying to identify what are the drivers of liking, right? So here we are converting these nodes into Boolean nodes, just true and false. We create our liking that we call the overall satisfaction in this case. And then we are going to generate an ICI network, right? So again, we are assuming that all these nodes, so that we have 18 nodes, they have an independent effect. So there is no interaction. If we think that there is an interaction, we need to manually create intermediate nodes, right? So we create this type of network. So as you can see, it's like more or less a kind of regression model here. And then we are going to use Helixia for the estimation of the probability. So usually when we have this kind of model in a brainstorming session, we have to use the knowledge of the expert in order to estimate the prior. So what is the priority of the root nodes, and then the conditional. So at the end of the day, what are the direct effect of each driver on the liking, right? So here we are going to use GPT here for that. And where's or not GPT, just I think I'm using 5, sorry. I've used a set of engines. So it's like having 5 experts in the room. And they gave me their feedback for estimating the direct effect. So for example, here, if I focus on classic timeless pill effect, when it's false, it has almost no effect for Google, a slightly negative effect for Anthropic, same thing for DeepSeek, same thing for Mistral, and same thing for OpenAI, right? And when it's positive, it has almost no effect for Google, 40% effect for Anthropic, 30 for DeepSeek, 40 for Mistral, and 40 for OpenAI. So based on that, we are building a consensus. And then we have we have estimated the effect of each drivers. So it's based on, again, same kind of information based on the information that is contained in the knowledge file, plus obviously the knowledge that is encoded in the deep URL, right? And then we do the same thing with the roots. So we're going to estimate what is the marginal probability, and now it's mainly on the knowledge file, obviously, because they are gonna count more or less. And then we have same thing. We can generate the report, and we have the probability distribution here that have been estimated, right? So you see, each engine return a probability distribution along with a confidence value, and so we are using these two pieces of information for computing the consensus. So exactly the same thing as what we do in brainstorming session with human experience. So here, if I click on this distribution, so that represents a consensus, I can see the different values that have been elicited by the NLM, right? So here you see they are in agreement. And if I go to a direct effect, you can see no yellow cells, so they also agree. Okay, and then I can use this network for sensitivity analysis and see what are the strongest drivers here based on these comments. And I can see that this is fresh nodes here that allows to improve the most overall satisfaction, it seems. And then, so you have this tornado diagram that shows the effect of all drivers. So when it's symmetrical with respect to the, let me go back to, when it's symmetrical with respect to the axis, this means that it's a symmetric effect. When it's on the left, it means it's a must-have product. And when it's on the right, it's nice to have product. Okay.
All right. Thank you very much, Lionel. What a fascinating topic. I'm really glad we have this recorded on video. I will certainly watch this again, perhaps multiple times, to capture all the nuances of what you said. Very, very interesting. Thank you. So I'd like to take you to France, to Paris more specifically, where Lionel will be hosting a Helixia course. Helixia is obviously much of what Lionel just talked about in the last portion of his presentation just now. So there you have the opportunity to go much, much deeper and learn about Helixia in practice, going through many examples, such as the one we just saw. Beyond in-person courses like the one in Paris, we also have more webinars come up. The next one is on June 26th. Lionel will also be the host. The title is Visualize, Navigate, Engage. And that is about publishing interactive graphs with BayesiaLab and HelixMap. That's a new feature which you may not have heard about. You are probably familiar with the web simulator that allows you to simulate with models that you've created and uploaded, but the web simulator just gives you a nice web interface to experiment with a model. HelixMap allows you to actually explore the structure of the model and visualize the relationships. So that is very, very powerful. I encourage you to participate in that webinar. Registration is now open. Then in July, we go into another marketing science topic titled Smarter Segmentation. And we will talk about Bayesian networks and Gen AI, how they can help decode consumer diversity. This is really about fundamentally improving the approach to segmentation, and I'll be the host of that program. And finally, to conclude, I'd like to give you an outlook on our conference in November in Florida. For those who live in the Northern Hemisphere, it will be a wonderful time to visit Florida because it is still nice and warm there. We have hotels that are located right on the beach where you can choose to stay. We were really looking forward to bringing the BayesiaLab community together again at this venue. We have a fantastic venue at Florida Atlantic University. So this should be really a great event, and it would be wonderful for you to join us there. So with that, I thank you for participating. Apologies for running over, but I'm glad many of you stayed with us. So thank you again and have a fantastic day.